The practice of science is being transformed by the power of computational processes for data collection and analysis. Computational modeling of phenomena has enabled new questions to be asked and investigated. At the same time, the role of computational thinking in science learning experiences is continuing to expand to better reflect the changing face of science. However, the field is only just beginning to unpack what cognitive processes are involved in computational thinking in science learning. We are asking questions like, what are the learnable elements of computational thinking that position youth for success with future learning opportunities and help advance them along academic and career pathways in science? In response to this need, our team has been working to operationalize the construct of computational thinking for science, to figure out how to reliably measure it and to deploy that measurement to better understand the extent to which engaging in computational thinking supports the process of learning and doing science.
We began our work with a review of the literature. We synthesized this with other frameworks and standards in CS and science education literature, with the goal of creating an actionable model of cognition that could ground assessment and instructional design. This is what we came up with, a framework centered on the cognitive processes involved in putting computational tools to work to achieve science goals. Leveraging this new articulation of CTS, we engaged in iterative cycles of evidence-based assessment design to develop an instrument that reliably measures CTS and predicts science learning. The measure is composed of 20 items, takes about 15 minutes, and psychometric testing has generated strong evidence for its validity with middle schoolers.
As UC Berkeley's Public Science Center, the Lorenthal of Science is engaged in active research about design and impacts of formal and informal science learning experiences at the intersection of computation and science. This new framework and assessment for CTS advances our work in this area. More broadly, our findings about the role of computational thinking in advancing science learning suggest a call to action to better and more equitably support CT learning opportunities. Science is increasingly computational, and our measure has shown that computational thinking matters for science learning. Our work demonstrates the importance of efforts to integrate CT into core science learning experiences so that we can broaden participation in science learning and discovery now and into the future.